Have you had the feeling that your bundle is getting out of control? Someone told you you had to work on your site performance and don't know where to start or what to do? Well, I had the same feeling some time ago. Last year in a big project, they asked us, hey, what about performance? I'm Matías Arabolaza, head of frontend at Baltec, and today we take a deep dive on how Lighthouse and web performance really work and how can it help you make your website lightning fast. Let's get into it. So this is the agenda for today. First, where to start, right? We will check the fundamental of Lighthouse, how to understand it, concept behind it, audit, etc. We'll go through by some metrics, why numbers are important, why speed is important too. Then the most common bad performance reasons, and finally, what we can do to fix them and possible solutions. But where to start, right? Well, it sounds like a basic question, but what is Lighthouse? Basically, Lighthouse is an open source tool for improving quality of web pages. Is there any alternative to Lighthouse or tool to measure your performance? Yes. Some of them are Creepy, Shitty Metrics, PageSpeed Insights, Yellow Lab Tools, and others. If you ask about PageSpeed Insights, this is slightly different from Lighthouse. For instance, PageSpeed is only evaluating performance and not accessibility, CEO, and others. So you can use Lighthouse to audit performance, accessibility, progressive web apps, best practices, SEO, and more. In all of these audits, you will have an overall score, areas to improve, and opportunities. But today, we will talk about performance only. And for that, we have to know how to understand Lighthouse. I think to understand Lighthouse, we have to know first the concept behind it. These concepts are used in several other tools, like the previously mentioned, right? We have six concepts or audits that Lighthouse is going to check. Some of them are more important than others or have more weight in the score. The first one is first contentful paint. This metric measures how long it takes the browser to render the first piece of DOM content after user navigates to your page. And what is the first piece of DOM? Well, it can be text, only text, images, non-blank and canvas element, and SVG. Anything inside an iframe isn't included. Before continue, sorry, if you wonder how to improve this, let me tell you something. Unless you have a specific reason for focusing on a particular metric, it's usually better to focus on improving your overall performance score and not only one specific reason. Sometimes you will notice or you will have the experience that you want to improve a specific reason and then you can decrease other scores from others audits, right? So at the first gap or first level, it's better to improve the overall score. Next one is speed index. These metrics measure how quickly content is visually displayed during page load. It is the average time at which visible parts of the page are displayed. Expressed in milliseconds and depending on the size of the viewport, the lower the score, the better. The calculations calculates what percent of the page is visually complete at every 100 millisecond interval until the page is visually complete. Speed index only takes into account the above default part of the page. This is directly visible by the user, right? As a consequence, this metric is highly dependent on the viewport size. Largest contentful pane reports the render time of the largest image or text block visible within the viewport. What is a good LCP score? Well, to provide a good user experience, sites should strive to have largest contentful pane of 2.5 seconds or less. I'm sorry. But, well, what elements are considered for LCP? Well, can be image elements inside an SVG elements, video elements, elements with background image load by the URL function, block level elements containing text node, or other inline level text element children. Now, yes, the next one is time to interactive. These metrics measure how long it takes a page to become fully interactive. So when a page is considered fully interactive, well, it can be when the page displays useful content, which is measured by the first contentful pane. Be careful here because you are having a metric. This is time to interactive that is depending or indirectly depending on other audit, right? Is in this case is first contentful pane. So then when event handles are registered for most visible page elements, and then when the page responds to user interaction within 50 milliseconds. Next one is total blocking time. This metric measures the total amount of time between first contentful pane and time to interactive. Again, be careful here because we have not only one, if not two metrics that are impacting in this audit that is total blocking time, right? So the main thread is considered a block anytime there is a long task. A task that runs on the main thread for more than 50 milliseconds. We say that the main thread is blocked because the browser cannot interrupt a task that is in progress, right? So in the event that the user does interact with the page in the middle of a long task, the browser must wait for the task to finish before it can respond. If the task is long enough, anything above 50 milliseconds, it's likely that the user will notice that the delay and perceive the page as sluggish or chunky. The last one is cumulative layout shift. These metrics measure the sum of all individual layout shift score for every unexpected layout shift that occurs during the entire lifespan of the page. So a layout shift occurs anytime a visible element changes its position from one render frame to the next one. That layout shift only happens when existing elements change their start position. So if a new element is added to the DOM or an existing element changes size, it doesn't count as a layout shift as long as the change doesn't cause other visible elements to change the start position, right? As you can see in the metrics, most important ones are total login time and largest contentful pane. Then we have time to interactive and first contentful pane and speed index with 50% of the score. And lastly, but not less important, is cumulative layout share. Right? So a super useful tool that Lighthouse provides us is the scoring calculator. With this tool, you can put your numbers there and see how the score is affected by this one. And you can play with the values to check what is the number that you need to get a green or just to improve some metrics. But this is a very useful tool to check how is your score doing and what you need to get successfully, right? Continue with the metrics. Metrics have color codes, right? As you can see, 0 to 49 is a red. It's a poor, bad performance reason, no, bad performance. 50 to 89 is orange, needs improvements. And green is 90 to 100. But why numbers are so important, right? So we have some metrics and numbers here. So we can see that, for example, 100 milliseconds is about the limit for having the user feel that the system is reacting instantaneously. Just only 100 milliseconds. Yeah, that's correct. And that's very snappy, super fast. So in 100 millisecond delay, inside loading speed can cause a 7% drop in sales. That's a lot. And in several cases, a lot of money, right? 47% expect a page to load in 2 seconds or less. And 40% of the users will abandon a web page if it takes more than 3 seconds to load. So yeah, some of you for sure are you going to abandon a page that is taking more than 3 seconds, right? So don't panic. In this section, we'll take a look at the main bad performance reasons and then what we can do to fix them. So first one is big bundles. Big bundles can be the main reason of your performance issues. JavaScript is parsed, compile, and execute in the main thread of the browser, which means the users have to wait for all of this before they can interact with the website. This might bring several problems. Super big network payloads, especially consider slow connection with some mobile devices. Your page will not be interactive until it loads. Parse time, modern JS engines are fast, but the more code you load, the more the browser must parse through, right? Execution time, the more that you want to execute, the more code that you want to execute, the longer it will take. Again, your page won't be interactive until much of this completes. And lastly, memory consumption, everything that take up a space, so the code itself, runtime variables, DOM elements, etc. So the warning remove unused CSS or remove unused JavaScript appears when Lighthouse has found too many CSS or JS code on a page that are not being used at the moment. Because of this unused code, the page loads slower than necessary. Why? Basically because there is unnecessary network traffic because the files or bundles are larger than necessary. Therefore, it takes longer to parse, compile, and evaluate the scripts before the browser can proceed with all the other work that is needed for rendering the page, right? As you can see, always large network payloads are highly correlated with long load times. In this case, you can see the metrics remove and use JavaScript affecting in a critical way the, the loading of the page, right? For example, suppose that you want to use Bootstrap button on your page. So to use the button component, you need to add a link to Bootstrap style sheet in your HTML like this. So this style sheet doesn't just include the code for the button component, right? It contains the CSS for all the Bootstrap components. But you are not using any of the other Bootstrap components. So your page is downloading a bunch of CSS that it doesn't need. Having a bad image strategy optimization can be the root of important problems too. So this will increase the network payload for sure, and it can increase the time to interactive. Moreover, image take up more than half of the page size. Then large unoptimized images will cause visitor to bounce, and in time, Google will notice as well, and it will affect your CEO for sure. This is not going to affect your bundle size, but it's going to increase your payload network. So what is the payload network? Well, basically, is that everything that the user has to download to have the page interactive. This can be JavaScript and CSS files, images, videos, etc. So based on the HTTP archive data, the media network payload is between 1.7 and 1.9 megabytes. So Lighthouse flags page whose total network requests exceed the 5 megabytes, 5,000 kilobytes, right? In some moments, we will check best way to improve this problem. So render blocking resources are static files such as fonts, HTML, CSS, and JavaScript files that are vital to the process of rendering a web page. So when the browser encounters a render blocking resource, it stops downloading the rest of the resource until these critical files are processed. So in the meantime, the entire rendering process is put on hold. On the other hand, non-render blocking resources don't postpone the rendering of the page. So the browser can safely download them in the background after the initial page render. So if you reduce the numbers of render blocking resources, you can shorten the critical rendering path and reduce page load time, right? Therefore, improving the user experience and search engine optimization. But I mentioned something before. So what is the critical rendering path? It is the minimum steps that the browser has to take from the moment it receives the first byte of the HTML document to the moment that it renders pixels on the screen for the first time. So essentially, it's what the browser has to do to process our critical resource into something that our user can enjoy. So which URL get flagged as render blocking resource? So it can be that a script tag that is in the head of the document, for example. a script tag that doesn't have a defer attribute, and a script that doesn't have an async attribute. For style sheets, we have the tag that doesn't have the disable attribute. So when this attribute is present, the browser doesn't download the style sheet. And we have tags that doesn't have a media attribute that match the user devices. So we can have like the attribute media set to print. So this attribute is not going to match our device if we have a laptop or we have a mobile phone, right? So this is only just for printing, but the browser is not going to download that style sheet. Well, not too much to say here, right? We all know that notable folders can get out of control very easily, right? So this third-party code generally refers to scripts embedded in your website that are not authored by you and served from third-party servers. Some examples, some examples can be social share buttons, video player, carousels, analytics libraries, helper libraries like date formatting, animation, functional libraries, and more. Whatever you can think about it, it can be a third-party library. So any significant amount of JavaScript can slow down your performance, but the main problem is that the third-party JavaScript code is usually outside your control and it can bring additional issues, right? So for instance, network issues. Setting up connections takes time, and sending too many requests to multiple servers cause slowdowns and latency problems. Extra parts compile and execute. As this is JS code, the browser has to parse, compile, and execute, and that could increase several audits. Another example is rendering. The way that third-party JavaScript is loaded matters a lot. So if this is done synchronously in a critical rendering path, it delays parsing the rest of the document. And in the previous slide, we talked about blocking render results. So, well, this could be a problem. If a third-party library is being loaded synchronously, it's going to block the rendering process. So, what we can do to solve these issues, right? Well, let's go through by puzzle and super easy solutions that we can implement in all projects. First, you have to know what you have under the hood, right? The bundles, the libraries, the code that is living in your application. There is no best way to know this as the bundle analyzer or any tool that you want to use to check uh, your bundle skeleton, right? We have several ways to know this, depending on the framework that you are using, React, Angular, Vue, or just vanilla JS. But we have a lot of options, right? In case of create React app applications, we have to use the source map explorer. We need another option, of course, but uh, so we have to install it with npm or yar, whatever you are using. Then add the script analyze to our package.json file, and lastly run npm run build and npm run analyze. So you will see a screen like this where you have all your bundles. We don't have colors, but well, it's a very easy way to know our bundles, the size, which orphan live maybe you are not using. So if you are using Webpack, you have to do something similar, but in this case, using the Webpack Bundle Analyzer plugin is a very good option. So similar as the previous example, you have to install it with npm or yarn, import this in your Webpack configuration, then include it as a plugin, and then when you run your normal build, it will create an interactive visualization of your bundles. As you can see, this option can be more intuitive since we have colors and another structure. It's a bit nicer, and you can zoom in and zoom out the bundles that you are using. So pretty basic and simple, but sometimes we forgot to set our project for production. Many libraries will key off the mode variable to determine what should be included in the library. For example, When the mode variable is not set to production, some libraries may add additional logging and testing to make debugging easier. However, with mode variables set to production, they might drop or add significant portion of code to optimize how things run for your actual user. So it will be much faster for sure. In case of Webpack, starting from version 4, it will minify your code by default in production mode. So if you are using an older version of Webpack, you will have to install and include, for example, the Tercer Webpack plugin into your Webpack configuration and run this by yourself. This is not happening create React app because that we only have to do is run yarn build that is going to build our project in production mode, right? So never is too much about compression, right? Right? When you go to production mode, Webpack is going to use Terser to minify your code. Minification does things like removing white space, removing comments, removing non-required semicolons, reducing hex code length, and stuff like that. So you can have a very simple code like this. This is normal JS code that you can write and read, of course. And if you minify that, it will look something like this. As you can see, the file remains perfectly valid code. You wouldn't want to try to read it or work with it, but it's not breaking any rules. The browser can read it and use just like it could be the original file. In this case, I assume that you can read it, right? I assume you don't want to read this one. Yeah. So compression is different. She find all repetitive string and replace them with pointers to the first instance of that string. This can be incredibly effective at reducing file size, especially with code, since it can be incredibly repetitive. On the web, shipping is done directly by your server. It's a matter of configuring the server to do it. So once that is done, shipping automatically happens. There is any there isn't any ongoing work you have to do. Just the server compress the file and send it across the network like that. So then the browser receives the file and unzip it and unzip it before using it. If you want to go further, you have Broadly. So Broadly is also an algorithm compression. It is developed by Google and serves best for text compression. So as you can see, it's 14% smaller than GC for JavaScript, 21% smaller than GC for HTML, and then 70% smaller than GC for CSS. It is supported by all major browsers, as you can see. It's not supported by IE and Opera Mini, but then it's supported by all major browsers. Anyway, put um, you can put a fallback for gzip if you want, so you can safely have an option if some browsers don't support this algorithm. So your application is growing every week. New features are being added, and its size constantly increase, right? So you want to provide great user experience, but downloading a lot of megabytes of the application uh, just to display a single screen doesn't seem right. Sure, I mean you can enable code minification and compression as we saw before, or caching mechanism, but eventually you will end up having the same problem. A large amount of data required to download to download to initialize your application. Code splitting with React or any other JavaScript library of choice is the answer of this exact problem. When it's worth it to use code splitting? So in particular, when you have a large JavaScript application, sorry, when you need to initialize the app quickly without using too much processing power, example maybe for mobile devices, or when the application has multiple permission groups or sections visible only to specific users, as well as any maybe other case. When you need to show different content depending on the user. So to understand when we should use code splitting, we can also remember the audit that we saw before, time to interactive. So when it comes to single page application, the time to interactive is often too long for the users to patiently keeping waiting. So how can we do this in a Create React application? We can start using dynamic imports. So to start doing code splitting, we have to use this feature that is coming from Webpack, ready to use in our React application. Doing something like this, Webpack is smart enough to split this in a separate chunk. If you are using a React app, this is already configured for us, and we can start using it immediately. So it's also supported out of the box on modern frameworks like Next.js. But if we want to do the same with a React component, from release 16, we can use React Lazy. Basically, the React Lazy function lets you render a dynamic import as a regular component. This will automatically load the bundle containing the other component, in this case, when this component is first rendered. React Lazy takes a function that must call a dynamic import. So this must return a promise which resolves to a module with a default export containing a React component. But the lazy component should be rendered inside a suspense component, which allow us to show some fallback content, such as loading indicator or an entire component that you want. So the fallback props accepts, as I said before, any React element that you want to render while waiting for the component to load. You can place the suspense component anywhere above the lazy component. You can even wrap multiple lazy components with a single suspense component like this. As you can see here, you can wrap several components inside only one suspense component. So if the other module fails to load, for example, due to network failure, it will trigger an error. So you can handle this error to show a nice user experience and manage recovery with error boundaries. Once you have created your error boundary, you can use it anywhere above your lazy component to display an error state when there is a network error. Error boundaries are real components that catch JavaScript errors anywhere in their child component tree. Log those errors and display a fallback UI instead of the component tree that crashed entirely. Here's an example of how to set up route-based code splitting into your app using a React Router with React Lazy. So pretty nice strategy because what you would load in your homepage, the code that you need in the about page, right? In this case. So the user is not going, if you go to your homepage, the user is not going to see anything about the about page until it goes to that section, right? So this is a super smart strategy just to not load any page that you don't need in a page layer level, right? Sorry. So, lazy load everything. Lazy loading is a strategy to identify resource as not blocking, not critical in this case, and load this only when needed, right? It's a way to shorten the length of the critical rendering path, as we saw before, which translates into reduced page load time. It can occur on different moments in the application, but it typically happens on some user interactions, such as scrolling and navigation. So you can lazy load JS and CSS files, images, videos, chunks, whatever you want. It can be lazy loaded. If the user never scroll to the point of the page that contains an image, then the user will never see that image. So it also never loads in the first place because it was never needed. So in that case, the browser is never going to download that asset. Based on the previous example, we can do something like this, or trigger this behavior whenever we want, when the user scrolls, clicks, or any actions. So as you can see here, Webpack is smart enough again to check that we have a flag that is using the state to show or hide this component, right? In case of images, we can use the native attribute loading, right? Setting this to lazy is going to lazy load the image automatically. Obviously, this is yet not supported by all the browsers. For example, Chrome, Opera, Edge, and some version of Firefox, it is supporting them, but for others, for example, IE, yes, IE, Safari, Opera Mini, and others, we have to implement some workaround or qualify like this one, where we have to put, in this case, the URL in a data attribute. In this case, we can use data source. So with this, the browser is not going to load the image. And then when we need it, we can swap up the data source with the real source attribute of the image to trigger the downloading. So uh, for sure, you know maybe some examples of this, but basically is that you can trigger this on a click or maybe on a scroll event when the user reach that position in case of images, and then you can swap this attribute just to telling to the browser that you have to download this image in this case. This can be used by I think for videos too. So the browser must download and parse CSS files before it can show the page, which makes CSS a render blocking resource. If CSS files are big or network conditions are poor, requests for CSS files can be significant and can be increasingly increase the time it takes for a web page to render. So for that, we have the critical CSS technique. This is a technique that extracts the CSS for above the fold in order to render content to the user as fast as possible. But what is above the fold, right? So this is all the content a viewer sees on a page load before scrolling. There is no universal defined pixel height or what is considered above the fold content, since there is a myriad of devices and screen sizes. So inlining extracted styles in the head of the document eliminates the need to make an additional request for fetch this style. And the reminder of the CSS can be loaded asynchronously as we saw before using the lazy load strategy. There are numbers tools that can automatically determine the critical CSS for a page. This is good news because doing this manually will be a tedious process. So it will require an analysis of the entire DOM to determine the styles that are applied to each element in the viewport. And that will be a nightmare. So image optimization with next gen format. So here, the opportunity section of your Lighthouse report will list all the images in other image formats, right? Showing potential savings gained by serving WebP version of those images. But what is a WebP format? Well, it was developed by Google, again, and it's designed to create smaller or better looking image compared to JPG, PNG, or GIF image formats. In this case, WebP lossless images are 26% smaller in size compared to PNGs, and WebP lossy images are 25 to 34% smaller. Some of the most modern frameworks are using this format under the hood. For instance, Next.js with the new image component, I think starting from version 10, is using this under the hood. And Gatsby is doing the same, transforming images to WebP on build time. Otherwise, you have to do it manually, convert your image to WebP, and then using them in your project. Browser support, yeah, it's not universally for WebP, but it's pretty wide supported. Anyway, similar savings should be available in most major browsers in an alternative next-gen format. You will need to serve a fallback, maybe PNG or JPG image for other browser support in the case. So we talked about this in previous slides, right? How can unused JS and CSS can impact in your website performance. So shipping unused JavaScript or CSS is a common problem in web development, and sometimes it's not an easy problem to fix. Why? Because maybe you have third-party libraries, you have some code that you don't know that is there. So basically, how can you know if you have unused JS or CSS code, right? So Chrome has a coverage tab for this. Please see the image on the right. So you have to open the DevTools, go to Sources, press the Escape key, and if you don't have the coverage tab there, so you need to click the three dots on the left, right, and select the coverage tool in that case. Then you have to reload the page and record it. There you will see the percentage of unused JS and CSS code. As you can see, you can filter, and then for the type of the file, JS, CSS, and then you will see in red the amount of code that you are not using. So we went through several important topics here. We checked the fundamental of Lighthouse, concepts, numbers, and metrics. Then we went through by the most common bad performance reason, and finally, possible and easy solutions. I hope you can increase your website performance with all of these tips, and I hope you like it. So until next time, and thank you so much.